R1 and R2, and Y is Y1 and Y2. These are vectors, right? And then what you see here is if I would multiply this out, what would I be getting? Well, if I would multiply Y1 inside, I would just get Y1 and I multiply it with R1. This gives me exactly this term out here. Then if I would, then this variable right here, I multiply Y2 inside and I multiply with R2 again, gives me exactly this term. So all of that part has been done by these two identities. And then analogously, what I can do is I can, well, okay, now it's a bit more tricky. Let's start with the last one here. What do I get here? Here I get R1 times, or R1 times R1 times delta 1. That is exactly the same that we get from here, right? Multiply by delta 1. And then the same, of course, also with this side here, with the delta 2. So, actually, let's do this. We have done this, we have done this, we have done this, and we have done this. So we're left with a few more terms. Then here we have the epsilon 1 that is multiplied by y1, y1 transpose y1. And here we have the epsilon 2 with the same y2. So what we're getting here is we're getting this guy and this guy. Right? So, okay, so we have done this, we have done that, we have done this, we have done that, we have done this, and that. So that means the only thing that is left now to verify are those, right?
Is this to compensate for the
yes, so exactly. Now here I put a 2, and there I just to compensate for them. And if I do them, what do I see here? Here I'm multiplying by 2, the 2 delta 1, and then here it gets multiplied with R1 transpose, right? And where do we have that? Well, we have it exactly here, and so I'm missing something. I hope we have everything now.
the compensation is
Yeah.
without the
Okay. Do you see it? Only you see this. No. Yeah. So we have indeed we have to compensate for this thing there, and then we are essentially done. Okay. Anyway, this is a way of writing it. No, I want to make it very only one. Now we give all of these names. We call it L, we call it M, and we call it N. Okay. And then what we do now is we say like, okay, let B be the largest singular value of L. Let C be the largest singular value of N. Well, this is kind of easy. What's the largest singular value of this of the diagonal matrix?
where the maximum of the above.
Yeah, absolute value. Yeah. And then here I actually go here because here for the A, but I want the minimum of these two diagonal elements. And there's a reason for that why we use minimum and maximum. Why do we use the maximum of this thing here? Well, because what we are doing is we just say like we are switching the minus to plus, and then we just say like maybe multiply by that. I've not done anything wrong, right? That's kind of stupid. That's something. And then what do we do with the other things? Well, here there's a minus sign. That's why I have here minus a times the 2 norm of y squared. Why is that true? Yes, diagonal, right? And then the other term I just multiply with something bigger, but because it comes to the minus side, yeah, so I'm getting just this. Okay, good. Now the last term here, I'm saying this is small equals to d times 2 norm of r times 2 norm of y. Why is that true? Without the left, yes, yeah, so it's essentially Cauchy-Schwarz again, right? Because you're doing R transpose times L times Y, right? Then the 2 norm of this is smaller equal to the 2 norm of R times the 2 norm of Ly. And then this thing here, the last single value is actually the induced 2 norm, right? So that's why we're getting here. We're getting this, right? just by definition of this induced norm. So we're getting this part here. Okay, this is all math. Now, what we can do is completion of squares. By just rewriting everything, you can just do some kind of completion of squares. That's why it's equality, right? So you can check now that this will be equal to that, of course. And then the last step is to just say, okay, why do we do completion of squares? Because now we have a squared with a minus sign in front. Hence, you can forget about this thing. So we are just left with these three things here. And they all add up to this. Okay? And now, finally, what we know is, okay, now if I integrate this thing, here we started, right? If I integrate this thing to c power minus infinity to t, then we know this is greater than or equal to 0. But I can also integrate this thing from minus infinity to t then, obviously, right? That's how this works. And in the end, we're ending up with this inequality because I can obviously put the integral over this thing to the other side. So I'm getting exactly this, so then I have this constant c. This constant c is just this constant divided by this constant, right? Nothing no magic here. And yeah, then letting t go to infinity, it holds for all t, letting t go to infinity, we've proven our result. I know it's ugly, but I try to still show it to you that it's true. I don't know how you feel about theorems that you don't have any proofs or anything. I don't like it. I'm very much against it. Just, I don't know, it doesn't feel right. It's like I'm using something but I'm not sure if it's true and why it's true. It feels very strange to me. That's why I'm showing it. Also important, you always need to know when to apply theorems, right? So when you have a proof, you can exactly see which parts I can tweak, right? You don't know that if you don't know proofs. That's why I'm showing it. Okay, break, 10 minutes. Well, because that's exactly these two things added up. This job, right? I just put them on the okay. But these have to be brought up. Yes, I said this. Okay, this is a condition. Yes, of course. This is a condition.